All right, welcome to the first afternoon session. This one is on DNSSEC. Our first talk is from Juan and Pallavi from Salesforce.
Okay, thank you, Robert, and good afternoon, folks. So I'm Juan, and this is my colleague Pallavi, and we're going to talk to you today about our plans to deploy, planning and efforts to deploy DNSSEC at our company. And in case you don't know who we are, we're a large enterprise and a cloud computing provider. All right, so here's a quick sketch of today's talk. We'll start by talking about our rationale for DNSSEC. We'll give a very high-level overview of our DNS infrastructure and talk about our DNSSEC specific requirements. And then we'll take you through a survey of DNSSEC offerings by managed DNS providers. And also point out requirements that they're missing for us. We won't mention any specific vendors by name. Our goal here really is to paint a general picture and to highlight missing functionality that we think is important for us. Okay, use case. Obviously, we believe in the security benefits of DNSSEC. And I would be shocked if I need to convince the people in this room of the benefits of DNSSEC. But we also have some very specific business needs. So we have many US government agency customers, and in order to provide certain types of services to those customers, we need to be in compliance with a set of security certifications, which I'm going to briefly describe. So FedRAMP and DoD certifications. It might be interesting to ask a quick question. How many folks in attendance today have heard of these or are familiar with these? You've heard of DoD. Okay, so okay, that's a stepping stone in the right direction. You need to know a little bit more, but here's some pointers to some literature you can read. But essentially, there's something called FedRAMP, which is the US Federal Risk and Authorization Management Program. That last word should be program, not framework. And essentially, they include a set of security controls, specifically SC 2021-22, which require DNSSEC and DNSSEC-specific requirements. They essentially include a requirement to deploy DNSSEC. There's also the US DoD impact level certifications. There are a number of levels here, IL 4, 5, 6. You can read up about them. But essentially, they in turn reference FedRAMP security controls as a prerequisite. So a high-level summary view of our DNS infrastructure. We have many DNS zones, and I don't know if this is unusual or not, but some of them are very large, like well over 1 million records each, and they're also rapidly changing. We employ the services of multiple managed DNS providers. Typically, for any given zone, there's 2 providers in use. We also have some leaf zones in parts of our infrastructure that are delegated to commercial load balancing appliances. And we do use several non-standardized DNS features. So generally, these are things that fall under the category of traffic management. So these are things like geolocated responses, GSLB, load distribution, probing and failover records, et cetera. And we have a large number of automated tools in use by various applications that we run that are making changes to the zones pretty much on a constant basis. All right, so we wanted to lay out some of the DNSSEC specific requirements we have. So our initial thought actually was, can we scope this project to apply to only the US government customers? So that means essentially by splitting them off into dedicated zones and deploying DNSSEC only in those zones. And this plan was ultimately reconsidered for 2 reasons. The first is that would have an immediate operational impact on the existing customers, which we wanted to avoid. But secondly, and perhaps more importantly, was the realization that our long-term plan was always to deploy DNSSEC for all of Salesforce, so why don't we just do that? And that's essentially the plan that we came up with. So signing all of the DNSSEC Salesforce core applications involves on the order of 20 to 30 zones. This turns out to be a relatively small portion of our complete domain portfolio, but it does include some of our largest and busiest zones. For signing algorithms, we need to deploy something that's widely supported and ideally resistant to attack by the strongest adversary. So that means we're looking at something like ECDSA or RSA SHA-256 with suitably strong keys. For authenticated denial of existence, we need a mechanism that provides zone enumeration defense. That means we're looking at either NSEC3 or something that provides the equivalent function of NSEC3. And continuing with requirements, we need to support some of the non-standardized traffic management features that I just mentioned. We need the ability to work across multiple providers at the same time. So this is an availability requirement for us because we need to be able to survive the complete catastrophic failure of any single DNS fighter. And of course, we need performance and scalability. Anything we deploy needs to be able to scale to our largest and most active zones with no appreciable performance degradation. So there are a couple of models we are looking at. The first is what we call serve-only, and that's essentially where we treat the managed DNS providers as secondary servers. So we run a master signing server, it signs zones and uses typical DNS zone transfer mechanisms to push out those zones to the providers. The main challenge with this approach is that this mode of operation typically cannot support signing of these non-standardized features. So that's why we're looking at a second model, which we're calling sign and serve, where we essentially use provider-specific APIs to push out zone data to them, and they sign and serve out the zone to the rest of the world. So this mode can support signing the non-standard features as well if the provider in question is able to do so. And I want to point out also that many providers actually can't sign these kinds of features. So the plan quickly is the first model we're going to be deploying for our really big zones, which essentially use only vanilla DNS features. And the second model we're going to be using for the zones with those traffic management features. And I will turn it over to Pallavi now.
Thanks, Juan. So in this section, we are going to talk about the DNSSEC capabilities of some of the managed DNS providers that we evaluated. These are some of the largest managed DNS providers in the industry today. And we have worked very closely and collaborated with them for the purpose of this study. So what we found was, based on our study, we categorized the providers into two broad categories. Those that pre-compute the DNSSEC signature over the zone records, and we'll refer to them as pre-compute signers, and those that do online or on-the-fly signing, and we'll refer to them as online signers for the rest of this presentation. We have focused on few key criteria that are important for our infrastructure, and I'll start with those. So one of the first key criteria that we had was zone signing algorithm support. And as you can see in this chart, the zone signing algorithm support is not consistent across the providers. So for example, in sign and serve mode, that is when the provider is acting as a primary provider, say provider A and provider F only support RSA 256 when they are signing and serving a zone. They do not support some of the newer algorithms like ECDSA P256, but they do support zones signed with ECDSA P256 when they are serving a zone or when they are acting as secondaries. Similarly, you can see provider B, provider E serve only can sign and serve zone signed with ECDSA P256. But they do not support RSA 256 for sign and serve mode. And at this moment, they do not serve zones signed by somebody else, or they do not support DNSSEC signed zones. So, and C and D support everything. So the support varies widely between the providers. So the zone signing, zone enumeration defense. Now, zone enumeration defense is another important criteria for us because ours are corporate zones, and we don't want those zones to be enumerated. So what we found was most of the pre-compute signers are able to do NSEC3 mode of signing, denial of existence. The online signers use something called, at least the online signers that we evaluated, use black lies mode of denial of existence. Although we found, which was a surprise to us, there was one vendor who still uses NSEC as the mode of denial of existence, and we have worked with them on this. So the next criteria for us is zone signing efficiencies. Our zones are large, dynamic, and receive multiple updates per day, per minute. So the efficiency of zone signing, the efficiency of zone propagation, all of those change propagation was important for us. What we found was the online signers are able to take the updates very fast, mainly because they do signing at response time and not at update time. So they are able to receive updates very fast. On the other hand, we did find that there are some pre-compute signers who are able to incrementally able to sign a single update versus signing the entire zone. So which was a good thing that we found. Though there was one pre-compute provider that we found who had to sign the entire zone for every single update, which was a bit of a surprise for us. So this was something important. The next criteria that we had is zone sizes support. Our zones are fairly large, like Shumon mentioned, they are fairly in millions, and they're already challenging the capabilities of our providers. So signed zones would be that much of a challenge for them. So we have worked with them, and what we found was in sign and serve mode, the pre-compute signers are not able to sign or handle zones which sizes larger than 100,000 records, though the online signers are able to handle zones larger than that. But the good thing we found was in serve mode, the providers are able to handle or they are able to serve zones that are pre-signed and of record size up to 2 million records, so which was something good that we found. The next criteria for validation, next criteria of evaluation for us was signature validity period. Now, signature validity period is important, of course, as you know, to prevent replay attacks. The validity period indicates how much time an attacker can replay old signed responses. On the flip side, if the signature validity period are smaller, then it puts that much pressure on the provider to re-sign the entire zone. So as we expected, what we found was the online signers had shorter signature validity period, about 2 or 3 days. Again, because they sign the responses at query time and not at they don't have to re-sign the zone, they don't have to worry about all of that. So their signature validity period are about 2 to 3 days. On the other hand, the pre-compute signers, their signature validity period was almost 15 to 30 days. Those are the providers that we evaluated had signature validity period of 15 to 30 days. As far as we found out, we did not find a provider who allowed us to configure the values of the signature validity period. So that was something that we found. The next is key rollover support. So ability for ZSK to go through automated key rollover was another important criteria for us, and we found that the support for all of the vendors was widely different. Some vendors, it was fixed, a weekly automated ZSK rollover period. For some vendor, it was a configurable one, where we can configure between months and even a year. For some of them, it was a fixed period of about 3 months, 6 months, that type. So ZSK support, automated ZSK support was there for most of the providers, but the time limit of the ZSK rollover was different. What we found was for automated KSK rollover, there is currently no support in any of the providers, and that's of course till CDS or CDNS key is widely adopted. That's not realistically possible. So the next criteria of evaluation for us was signing non-standard traffic management record. As Shumon mentioned, we have zones that have traffic management records like GSLB records. We have records which are failover records. So where the response depends on real-time data. So what we found was the online signers are able to sign these responses, but most of the pre-compute signers are not able to sign the traffic management records because they already have the data and they pre-compute those signatures. But although we found, and which was a very good thing that which was a really nice surprise for us, was there was one pre-compute signer who is able to sign traffic management records. What they do is they pre-compute signatures across all possible answers, and that's how they can manage to sign traffic management records. The next criteria of evaluation for us is chain of trust. We have multiple zones and subzones. So secure delegation of the subzones was an important thing for us. What we found was there were 2 providers who do not accept a child DS record through any of their interfaces, though one of the providers, of course, worked with us and was able to accept a child DS using backend DB channels, but they did not have that support upfront through their interfaces. Though most other providers did have the ability for us to add DS record of the child into the parent. On the other hand, in the serve mode, most of the providers are able to serve the DNS zones which are signed and which have DS records in it. So this was another interesting result that we found. This is the last criteria, authenticated zone transfers. So DNSSEC is not designed to protect the transfer of an entire zone because a zone can contain delegation records, it can contain glue records. So having a channel security mechanism like TSIG is important. What we found was, and this might be a surprise for everybody, would be for inbound zone transfer, all providers that we tested support TSIG widely when they are acting as secondary. On the other hand, when they are for outbound transfer, outbound zone transfer, 4 out of 6 providers do not support TSIG when they are acting as primary. So that kind of doesn't gel well when you're trying to do multi-provider type of thing. So these are just some surprising results that we came across that we wanted to bring to this audience. So what are the conclusions from this? From our point of view, not a single vendor was able to satisfy everything that we wanted from our DNS infrastructure. So we have worked very closely with our vendors because even for them, these are new requirements coming, or these might be requirements that they are aware of, but just from priority point of view, may not have got prioritized. So we helped them prioritize some of these requirements. So the feature enhancement request that we made of our providers was support for DNSSEC as secondary, ability to do NSEC 3 when they are primary signing, ability to sign traffic management record, automated ZSK rollovers, and all of that. So now I'll hand over to Shumon for the next part.
Okay, so I mentioned we had a requirement for multiple providers. And so the serve-only model, where we're treating the providers only as secondary servers, it's pretty easy to support DNSSEC in that mode. I think it's well understood. The challenge comes from the requirement that we have to support the sign and serve model for the traffic management features. Those generally can't be served with a serve only because they require things like querier-specific responses or responses that have to be determined and decided at query time based on examination of some sort of dynamic state in the network. So those really have to be signed and served at the managed DNS providers. If we introduce the requirement of multiple managed DNS providers here, that's the novel thing that most DNS providers have not yet contemplated. So a very common response we got when we asked about this is, that's very interesting, but we've actually you're the first person to ever ask us for this. The good news, on the other hand, is a couple of them that we've talked to are very interested in making this work, so we'll see how that goes. The key challenge here is that since each provider signs and serves a zone independently, we have to very carefully manage the contents of the DS and DNS key RR set in such a way that validation is possible no matter which provider you query and obtain the response from. It is, however, certainly possible to deploy configurations that do this. In the next 2 slides, I've sketched out a couple of models which we think will work, and we've also vetted with the providers. In the interest of time, I'm not going to go through them now. I'll just leave them for your review here. But I will mention that we have also very recently just put out an IETF draft. There's a link at the bottom of the slide here where you can read about this and other models in more detail, and we'd be very interested in your review and feedback of that document. All right, so let's tie up, I think I'm running out of time, let's tie up a few loose ends. So we do also have, we have not only managed DNS providers, but I mentioned we also have in some data center designs, some leaf zones delegated to commercial load balancing appliances, and we need to do DNSSEC here too. The good news is that several commercial load balancer appliances do seem to support DNSSEC. However, this is a new area for us. We've just started testing, so we don't know how well they work yet. So I hope to report back on that at a later time. And wrapping up, so we had a set of DNSSEC requirements which we thought were pretty standard for a large enterprise, and it turns out that we couldn't really find any managed DNS provider that was able to support all those features comprehensively enough. Multi-provider DNSSEC signing is a more novel requirement that some of the vendors are just grappling with. And I want to finish off with a set of questions. So are other enterprises or companies facing similar requirements, number one? Number two is lack of DNSSEC demand in the industry, either real or perceived. Is that a contributing factor here? And the third question is how can we as a community, what can we do as a community to improve the state of DNSSEC offerings in the field? And that's about it. I will stop here, and we'd be happy to take your questions.
Hi, Paul Hoffman. Thank you. And to answer one of your last questions is the lack of other people needing DNSSEC. Yeah, that's why you don't have providers who already thought of this. My two questions for you are, when you kept saying you had problems with your traffic management, traffic being signed. Was that because you're using a different, is that because you were using a different query type, or is it because everything has to be done so rapidly?
No, it's because for the traffic management records,
yeah,
so
why
remember
were those
these are,
special?
it's not a different query type. It's a standard query type, but the way the response is generated is dynamic. It depends on the query location, or it may depend on the authority of a server having to do something, like look at the state, is this server up or is it not, and then I'll take it out of the response set of addresses that I return in the response pool, or things like that. So those kinds of things, if you have a configuration where you run a master server and you're pushing it out, you can't do it because the DNS zone transfer mechanism has no way to transmit that information, number one, and there's a few other problems.
Okay, great. And my other question was, for you, why was zone enumeration, why did it have to be NSEC 3 instead of NSEC? Why do you care about zone enumeration?
Yeah, okay, very good question. So let me be careful about how I answer this, because I haven't vetted this answer with anyone else. So you can imagine that a corporation may have many different types of DNS records. Some of them may be associated with specific customers or specific entities that they don't want to mass divulge to the world by trivialing or allowing the entire contents of their zone to be enumerated. So I'll stop there. But I can talk to you offline in more detail. Hello, Dwayne.
Hi, Shuman. Dwayne Wessels from VeriSign. I promised you I'd ask a question after your talk, so I was really excited when I came up with a good one, but then you sort of answered it at the end of your talk. So. But my question was going to be around features that you're looking for in a provider, and I was thinking that it would be good to have the ability to plan for stopping using a particular vendor, basically rolling out of a vendor into another one. And I think your ideas about multi-vendor support sort of solves that. So even if you didn't, if somebody was not using two vendors, those same features are needed when you want to stop using one vendor and stop using another vendor. You need to exchange keys with them and that kind of thing.
Sure.
So in terms of a question, have you done any work actually implementing that kind of stuff? Have you done tests with multi-vendor support and sharing keys and that kind of thing yet?
Yeah, so we've done a little bit of testing. We haven't tested a complete configuration yet because it requires the cooperation of some of the parties that I mentioned.
Well, but you could do it all in a lab setting or something.
Yeah. So in a lab setting, we've tested at least one of the models, not the second model, I think the first model, and it does work, right? So, I mean, it's kind of obvious if you think about how it has to work, how it should work. Your question about migrating mechanisms to migrate providers is very important. So the draft that we've written goes into a little bit more details about how to support this multi-signing, multi-provider configuration in steady state, right? So there's another component about doing key rollovers, which are also a steady state configuration, and there's a third component about how you migrate from one provider to another, right? So I think I have a placeholder in the draft for that, so I know it has to be solved, but we haven't actually thought through the detailed configuration steps in order to do it properly. Of course it can be done, but it has to be done carefully, and you can't, like, you know, if you don't do the set of steps in the right order, you might mess things up.
So we're going to cut the mic line at this point.
Pallavi, do you want to come up?
Rafael Akamai. So you talked a lot about the ways of non-standard ways of doing sort of some traffic management. Now, can you maybe elaborate on this a bit, and can you think of ways to maybe make them standardized?
Yeah, that's a very good question. I've been thinking about that for a while now, but Ralph, are you willing to help us start this conversation in the IETF? So I think it's a reasonable question. In the past, I'm sure this discussion has happened in the IETF. The pushback that you generally get is that's not how the DNS works. It's not the original DNS, the vanilla DNS at least didn't support a mechanism for query-specific responses or different types of responses depending on the network, the state of the network environment, right? So, but the reality is large enterprises, you heard the Facebook talk, they do lots of traffic management too. Lots of people in the industry do it. So I think if we need to get DNSSEC deployment to happen in complex enterprises, this has to be solved, and standardizing it would probably be a good way to help that. So thank you for that comment, Ralph.
Hi, my name is Andrew Sullivan, and I don't speak for any employer. You asked this question about whether it's customer demand and so on that hasn't led to all of this, and I would suggest that maybe this room ought to think a little bit harder about the answer that you got to that, because of course it's not just demand. I wouldn't ever want to contradict any colleague of mine, but at the same time, I'm a little skeptical that you were the very first person ever to ask for that feature. And so I think that what probably is true is that most of the companies who are doing this find that there's not a lot of commercial demand for this. And that's a different problem, because it's, as you say, it's a fairly complicated sort of space, and you're going to have to get this just right. And if you mess it up, you're going to have a lot of egg on your face, and you're getting $0 for that. So that's a real problem in terms of selling it inside any corporate environment, I would imagine, if I worked in one.
Okay, thanks for that comment. So I know we're running out of time. We'll just let it go. Right. So I was going to say, in response to Andrew, that so I'm just paraphrasing what the two vendors that I talked to told us that they haven't heard of it. I mean, I was surprised by that answer myself. Yep.
Hi, I'm Robert Martin Lejeune from PCH. You mentioned you were using one ZSK per DNS provider for signing. Of course, it creates a big apex. You could do something that would be considered heresy and just create a ZSK that you send to all your providers. You probably have a secure channel anyway.
Yeah.
And then tell inside the zone, put which key to sign with. I don't know.
Right. That's a good point. I did have this conversation with some of the vendors, so I think I got some resistance from a few of them saying that they're actually not willing to share signing keys with another party with which they don't have a contractual relationship.
I can imagine, yeah.
Okay, all right. But it's certainly a model that might work in some hypothetical scenario if everyone agreed to it.
Hi, Federico Neves from Nick.br. I saw your slide talking about KSK rollovers and the answer, but I'm still tempted to ask. And have you talked to vendors regarding algorithm rollovers support?
Not yet.
And
it's on my list.
Besides of that, any vendor supporting new algorithms, EDDSA?
Right. So we haven't broached the subject on the very latest algorithms. So ideally, we want them to support at least RSA and ECDSA. We haven't. I don't think any of the quick answer, as far as I know, none of them support add DSA to 5519 yet, but it needs to happen. Right. Okay, any others? All right. Thanks very much, folks. Oh, and by the way, I wanted to mention, this is Pallavi's first DNS OARC, so she wants to meet some folks, so if you have time and you want to introduce yourself, that would be great. Okay, thank you.
All right, so our next presenter is Petr Speček from CZNIC.
Oh. Okay. This is magic. Hello once again. Half a year ago, we were talking about effectiveness of aggressive caching versus hosting root zone on loopback, and the previous talk was based on theory. Now we can look at some hard data. So first, we'll go through the expectations from the aggressive caching, what we have promised in the RFC, and then how the reality looks like when we focus on the normal traffic and the random subdomain attack. Here, the RFC promises a couple things. Vaguely, it talks about increasing performance, whatever it means, and it can be translated to decrease in latency perceived by the client, decrease in resource utilization, whatever resource it is, it's not specified in the RFC, increase in privacy, which is for now out of scope of this talk, and increase in resilience. So let's look at the details. How effective it will be depends on a couple of factors. First, it's the query pattern, right? It's super different case when we get the normal traffic with normal names, which repeat, and so on. And this normal traffic is very different from the random subdomain attack, where every query is basically unique with very high probability, so the caching doesn't help at all. But that's not everything. The distribution of the names in the namespace in the zone under attack, let's say, also affects how effective it will be, because it changes the probabilities that you will hit the same section or interval in the cache. Of course, presence of wildcards and how we deal with wildcards is important, and it's DNS, so TTL is everywhere. So during the talk, we will be changing all 4 parameters and looking at the result. So first, normal traffic. That should be the place where we expect some little increases or decreases in resource consumption. So experimental setup, just quickly so we don't dive into very gory details. Surprisingly, I was measuring this on bind 9.12.0, which and the reason is that we already implemented the aggressive caching into NOT, but we decided that it will be enabled and that's it, because we don't like having knobs, and bind has different approach. So for my measurement, it was very nice that I could use stock bind without any patches and just flip a switch in configuration file, which was super convenient. The test basically consists of replaying the normal traffic to bind with different configuration, and then capturing the traffic between bind and the authoritative servers, and between bind as a recursor and the clients, and then analyzing what we got in those PCAPs. The metrics here are number of packets between the authoritative servers and the resolver, bandwidth, which is just sum of sizes of the packets, and latency for the answers. So data set, again, the query pattern is very important for this test. So I was looking for some real data, not made up queries. So I just took PCAP from our public open resolver, which we run at CZNIC, took 2 hours of the traffic and replayed those. it's approximately 2,500 queries per second, and I was intentionally excluding Q-type any because that's some attack which is going on in the background, and that's not normal traffic, right? So I wanted to focus on the normal traffic, so Q-type any was excluded. And after exclusion, it's again 2,500 queries per second. Approximately 14% of answers to these normal queries result in NX domain. So this is the portion of the queries which should be affected by the aggressive caching. And approximately 3% of those end up with serve fail, and it's mostly broken reverse zones. So it's not that interesting. Okay, tools. I will not go to details, it's just bind on machine with a huge operating memory, so the cache is basically unlimited. The rule written by Jerry to replay the traffic, thank you for it. DNS collector, which is a new tool written by cznick to be released, and libtrace to analyze number of packets and so on. So, first promise of the RFC is decrease in latency, right? So, do we have something to point at the slides? Finger. Okay, maybe mouse cursor? No? Okay, so I will try to describe, bear with me, please. So, at this graph, on the horizontal axis, we have the percentile of the queries, and at the vertical line or axis, we have latency, both are logarithmic. The graph reads basically that 70%, the green line reads that the 70% of queries is answered with latency below 1 millisecond, basically. That's how we read it. And surprisingly, the green line is without aggressive caching. And the blue line is with aggressive caching enabled in bind. And for some mystical reason, the latency here increased a little bit. So without the aggressive caching, the latency for 70% of queries was basically below 1 millisecond. And with aggressive caching, only 60% of queries was answered below 1 millisecond. So for some reason, the latency increased. But yes, it's weird. I double-checked that I didn't change names in the key. So it's reproducible. I don't know. It might be bug in some measurement tool, of course. In any case, my personal conclusion is that this is not super important because the increase is in a scale of milliseconds. So for eyeballs, it's not super important. Okay, that was about latency for normal traffic. When we look at, so this promise wasn't fulfilled, let's say, because we didn't observe the expected decrease in latency. On the other hand, in fact, we got some decrease in number of packets and bandwidth consumed by communication between the recursive resolver and the authoritative servers. So the promise of lower resource utilization when we speak about network utilization was fulfilled. So for the normal traffic, the latency didn't change in super significant way. I think that eyeballs will not notice. And the network utilization went down a little bit. And this boils down to the percentage of answers with R code NX domain and the number of signed domains and so on. So this was for the normal traffic, and now something more interesting, or at least with more fancy graphs. The random subdomain attack is basically the perfect showcase for aggressive caching, right? So the experimental setup here is a little bit different. We have one authoritative server, which is hosting zone, which is signed using NSEC. And then we have random or pseudo-random queries, which we replay to the resolver, which is going and asking the authoritative server. Now we focus on the communication between the authoritative server and the recursive resolver because the latency is not important, right? That's what attacker gets, and we don't care that much about it. Tools. Finally, some not tools. So the authoritative server was not DNS configured to sign the zone file using RSA SHA-256 algorithm and 248-bit keys, which of course generates large answers, and that was on purpose. And the resolver was again configured with basically unlimited cache. In practice, it was 20 gigabytes, but we didn't exceed this. So for the purposes of test, unlimited. DNSPerf was replaying queries, and again, libtrace analyzing number of packets and the bandwidth. The query pattern. These are pseudo-random names, and the important thing is that there is 256 bits of entropy in each and every name, so it's super unlikely that for the duration of the test we will hit the same name again. So the cache doesn't kick in, and that's basically what the attacker wants to do. And the DNSPerf was simulating 1,000 clients, so basically it's 1,000 threads where next query is sent right after receiving answer to the previous one. So one query after the next 1,000 lines in parallel. And now I return back to the beginning. Effectiveness very much depends on the data. So it depends on the zone file and TTL, presence of wildcards. So we have unsigned zone, which is a baseline for the measurement. The content of the unsigned zone basically is not important because we are asking for names which don't exist, so it doesn't matter. And then we have signed zones with different TTLs and different name distribution. Now, it's important to know that a generated zone will have different distribution of names than the real zone. So I was using real zones we have for testing. It was small block site with wildcard, Czech University with 14,000 names, smallish TLD with more than 100,000 names, and one TLD unnamed with 1 million names. Okay, so now we will go through the results of measurement and compare the results for every scenario with the baseline. This is the baseline with absolute numbers, and the absolute numbers in here are not practically important because we are interested in the decrease, not in the absolute number, right? If I had hardware which was more performant, faster, the absolute numbers would change, but that's not interesting. Maybe only one absolute number, which is cache size, which is right below the lines. You can see that after 1 hour of test, the cache size consumption was almost 20 gigabytes, which effectively means that if this attack was real, all the data from the cache would be purged and replaced with these nonsense queries. So the hit rate on the real resolver would be basically 0, even for legitimate queries. Okay. This is the same chart, but with relative numbers, and that's what we will be using in the rest of the presentation. So on both vertical axes, we have 100%. Cache size is again 100% for unsigned zone. Now, let's look at the results, finally. For the little zone with 50 names, 1 wildcard, and TTL, 60 seconds. Effectively, after 1 second, which is the only point in the graph in the top left, you can see that all the data get to the resolver's cache in the first second, and there is nothing. The communication stops, which is very different than 40,000 queries per second going, or packets going to the authoritative server. So for the small zones, the attack is basically stopped, and that's it for a duration of TTL. You can see that the cache size, which is right below the key in the graph, is, or cache consumption, let's say, is negligible. It's just nothing. So the resolver, even though it's under attack and is getting a lot of queries, it still can at least answer the queries, legitimate queries from the cache. So it helps on the authoritative side very much, and on the resolver side as well, because the resolver now can answer at least something from the cache, even though the CPU will be 100% utilized and so on. But that's attack, that's how it works. Okay, so let's look at a little bit bigger zone with 14,000 names. You can see that after 10 seconds, basically the communication between the resolver and the authoritative side is again almost zero, negligible communication. The interesting thing here is that even in the first second, the number of packets is about 8% when we compare this attack with the scenario with the unsigned zone. And even though we signed with RSA SHA-256 and 2K keys, so we signed the zone and generated large answers with large proofs in NSEC records, still the bandwidth consumed in the first second is less than 30%. So even though the zone is now much bigger, the bandwidth consumed by the attack is significantly lower when compared to the unsigned scenario. Okay, so 14,000 names, it's still very good. Let's try a little bit bigger zone with 110,000 names and 1 hour TTL. After 10 seconds, it's not that perfect because it's a lot of data, but still, even in the first second, the number of packets is about 18% of the original situation, and the number of packet bandwidth is less than 80%. So still, even for the huge zone, we are still saving bandwidth and number of packets when we compare the situation with the unsigned zone, which is, I think, super interesting. Okay, when we look at the longer time scale, now it's 1 minute, we can see that after 1 minute of the attack to this zone, we have approximately 1.5, or let's say less than 2% of number of packets between the recursive resolver and the authoritative side, and we have about 5% of bandwidth, of the original bandwidth. After 5 minutes, it's again going to zero. So now it very much depends on TTL. If the TTL is long enough, the attack will be basically stopped on the recursive resolver, which implements the aggressive caching. Now, again, please note the number about cache size. It's less than 1% of original consumption. So even though the zone is quite big, still the resolver, if it has sufficiently large cache, it can keep its data for the legitimate queries. Okay, let's try even bigger zone. 1 million names, 1 hour TTL. In the first second or two, we have about 1/4 of packets, or number of packets, exchanged between authoritative side and the recursor, and less than 90% of bandwidth consumed, which is, I think, very nice because we didn't find a case where the bandwidth exceeded the case with original zone. Okay, so after 10 seconds, numbers are going down, but not that much. After 1 minute, it's more interesting. After 1 minute, we have about 5% of number of packets and 20% of bandwidth. Let's go at even larger time scale. After 10 minutes, we are slowly approaching zero. And after 1 hour, there is, again, perfect zero, or maybe after 20 minutes. Again, cache size is significantly lower, so the resolver can keep some data in its cache and answer legitimate queries. Of course, for the large zone, the TTL is super important because there is a lot of data which need to get to the cache until it's effective. So let's try something else. If we shorten the TTL to 60 seconds, which is a zone with, for a zone with 1 million names is, I think, well, I shouldn't comment on that. Guys from Salesforce know about this more. So I refer to the previous presentation. Anyway, after first minute, you can see that, of course, there is a spike on the graph because a lot of the data which we got expired at the same time, but the important thing is that over time it will smoothen and it will approach slowly something like a line around 10% of packets exchanged between the resolver and authoritative server, and approximately 35% of bandwidth consumed by the communication between the resolver and authoritative server, which is, I think, super nice for 1 million names with so short TTL. Cache size is also the same, less than 1% of original consumption. Okay, so we can conclude that for the random subdomain attack, the promises of aggressive caching as written in RFC are fulfilled, because it definitely lowers resource utilization at the resolver, because the cache is not filled with nonsenses, and network utilization and the communication between auth and resolver is significantly lower. Okay, so to answer question, the subtitle I think is definitely worth if you use NSTAC, of course. For the normal traffic, the difference is, I would say, not significant, because the decrease in the traffic is, well, maybe 1%, maybe 3%, depends on metric, and depends on how much traffic you get, but that's not super important. For the random subdomain attack, is definitely worth, because it can stop the attack, or not stop, but confine the attack to the recursive resolver, and it improves at the same time situation for the authoritative side, that's obvious, but also for the resolver operator, right? Because the hit rate ratio will be significantly better than without the signed domain and the aggressive use of caching. All this applies to zones signed by NSEC, because right now we don't have implementation for NSEC 3, but that's on the way. So we'll see what happens when we implement support for NSEC 3 aggressive caching. We have to measure this. Maybe the numbers will be different because CPU consumption might be higher on the resolver or something. We'll see. So you can look forward to Not Resolver 3.0, which should be released soonish, and which will have support for NSEC 3, and then look forward to some measurements. Thank you for your attention.
Hi, I'm Warren Kamari from Google. He would like to thank you for this, because he's sitting here gleeing at the whole time. He was like, yay!
Yeah, and actually Warren Kamari from Google. So yeah, seriously, thank you. I was kind of concerned when I saw your first slide or two with the latency increase. I was like, this is going to go poorly. But thank you.
One good follow-on would be to, this is Wes Hardiker from USC now, sorry, is to actually compare CPU usage. So, if we could see a graph of the CPU usage on the resolver, at full blast, where it's suffering, attacks with and without DNSSEC validation to get
well,
that.
Well, on the resolver, it's just, 100% utilized, because you just push as many packets as you can. So, but for the NSEC 3 support, I will definitely measure CPU consumption, because it will get more interesting. And let me reiterate that I'm not really sure what happened when it comes to latency in the normal traffic case. It's just weird. So maybe it was a problem in measurement. I don't know.
So one of the other things that I've been doing for a test in the last couple of months myself actually is measuring packet loss rate for a resolver. So not if the CPU is 100%, you're right, that's going to happen. But there are tools that you can use to fire traffic, and it will tell you how many responses it didn't get, so you can actually measure, the resolver may be dropping a huge amount of traffic from clients that it's not actually getting.
Yes, I can say that in this test, the test setup was such that it wasn't dropping basically anything, because the DNS perf was sending next query after receiving answer to the previous one. And the drop rate was negligible, well below 1.01. again, 0.1%.
I am Kazunori Fujiwara from JPRS. Thanks very much for implementing RSC 8198. And the reason of small difference is that there is small ratio of signed domains, signed query names.
Yes,
and
that's correct.
Most of TLDs use NSEC3 opt-out. So opt-out may not be good. And please count queries for root servers. Queries to root may be decreased well, I think.
Yes, when we talk about opt-out, or my question is, what's your question now? Or if I should just comment. Do you have some particular question, or can I just expand on this? Okay. When we talk about NSEC3, of course, when there is opt-out, aggressive caching doesn't work because there is nothing signed in the interval, right? But TLDs are not the ones who fear most from the DOS attacks or random subdomain attacks, right? So TLDs can typically handle the load, this aggressive use of cache. Well, more or less. Jeff has its doubts, but this aggressive use of cache could very much help to the small guys because it confines the attack to the resolver and it doesn't get to the authoritative that much. And yeah, we'll see how it goes when we implement support for NSEC3.
So Warren Kumari, Google, I think to expand on Fujiwara's question, if you do this stuff again, can you have a look and see if there's a decrease in queries to the root server in particular, because it's sort of a standard type of zone that's signed with NSEC, and it might be a good representative example, maybe.
Yeah, this was topic for the previous presentation, and I think that the numbers there hold, so I will not worry with it again.
Ralph Wilmans, NL Labs. Did you set the CD bit on those random subdomain queries?
No.
Because I think there are resolvers that do not set the DO bit on outgoing queries when the CD bit is set. So that means you won't get NSEC records anymore, and you can still do the attack.
Well, yeah, that's the implementation detail. Up to the resolver what it decides to do, if it asks the authoritative side with DO or CD or whatever. But we use the bit, so we get the bruise. Thanks.
All right, our next presenter is Roy Ahrens from ICANN.
Thanks, everyone. My name is Roy Ahrens, work for ICANN. This presentation is about the curious case of the crippling DS record. And forget the title for a second. It's really a public safety notice. Something happened in December where 3 top-level domains failed validation. I didn't find this myself. It was my good friend David Soltero from the DNS engineering team who alerted me to this. And I had a quick look. And it's actually a very interesting case. So this presentation, I will talk about these validation failures. We'll explain on a high level because you all know how a KSK is rolled, right? And it's specifically about double DS. I'll talk about when double DS fails, what the standards say about that, and I have some notes on the chains of trust that I talk about. Also, this will become clear in the end. What is this trying to prevent? And of course, some advice. Might not be good advice, but hopefully we get a discussion about this. So this is a fairly short presentation. Hopefully I get it under 15 minutes so we have time to discuss this. So like I said before, David Soltero pointed me to this situation. And when I checked, there wasn't a problem at all, right? I checked with Dig, and there was a there was a chain of trust. A chain of trust in this case is nothing else than a self-signed KSK in the child with a DS in a parent pointing to it. Self-signed here is important. What I mean with self-signed is the KSK that's part of the key set, and the key set is then signed with that KSK. That's what I mean with self-signed KSK. So when I checked, there was these all of the records needed were there. And so what I did notice was, I didn't notice that David actually told me this. This was part of a KSK rollover in the child. And so this happened when DS records were added to the parent. And what stunned me completely is that this is actually protocol compliant, strangely. And I'm a little bit annoyed by this because it was completely unexpected. So, really quick, high-level KSK rollover overview for double DS. You always need to have a chain of trust when you roll from the old key to the new key, right? You don't want to go unsecure, you don't want to go bogus. So you want to have this chain of trust in place. So, as I said before, the steady state is you have a KSK, a self-signed KSK in the child with a DS pointing to it from the parent. No sudden moves, right? You slowly add a new KSK in your child zone, right? You do nothing, you just add the new KSK in the child zone, and you wait for a while. Then you add a DS record with a hash over that thing in the parent, right? You step back, you do nothing, let it propagate. And then at one point in time, you sign the DNS key R set with a new key instead of the old key. And all that's left is a cleanup, right? You need to remove the old stuff. Now, this is a little bit too much text, so I have nice graphs. On the left-hand side, you have the parent, right-hand side is the child. This is steady state. Self-signed key on the right-hand side, DS pointing on the left-hand side. All is good. Green in this case is good. Red is bad, and we can get to red in a second. So we add the DNS key number 2, right? This is the first part of a rollover. Excuse me? Why is that bad? No, that's not bad. Sorry. You're absolutely right. Thank you for pointing this out. Green is good, as in this is a chain of trust, right? Merely having a DNS key in a zone doesn't mean it's part of a chain of trust. In effect, just to prevent people from standing up and correcting me here, the DNS key number 2, right, is actually can actually be authenticated because it's part of the key set that is self-signed by DNS key number 1. What I mean with chain of trust is DS on the left-hand side, on the parent side, and a key on a key in the child side that is self-signed. So the DNS key is not self-signed, that's why it's red, right? You now add a DS on the left-hand side, on the parent side, still red, right? It's not bad, it's just not a chain of trust. And poof, now we have a secure chain of trust, right? And what's left is the cleanup. So you remove everything, and you're in steady state again. You have DS2 pointing to key 2, which is self-signed by key 2. So when does this go wrong? And I'm using specifically DNS-VIS because everyone recognizes DNS-VIS. I had to use DNS-VIS in order to have it explained to me what went wrong. So on the left-hand side, sorry, not on the left-hand side. Now on the top half, to make it more complicated, you have... You have a DS record with type 1. This is digest type 1. This is SHA-1, to be clear. Pointing to a DNS key, which is self-signed. There's that little arrow on the side. That means self-signed, if that wasn't clear yet. Now you add a DNS key. DNS-VIS draws a nice arrow to the DNS key. That means DNS key 2 can be authenticated by DNS key 1, which is trusted because you have a DS record. Excuse my French here. So far, so good. Now you add DS type 2 and type 1. So two records to the root zone, or sorry, to your parent zone. Type 1 is, of course, SHA-1, and type 2 is SHA-2 or SHA-256, depending on which crypto hat you're wearing. And if you look at this, this is actually good, right? Even though on the right-hand side is not a chain of trust, you still have a chain of trust of the left-hand side, right? The DS pointing to the DNS key. But you're not a validator, right? Validators see it as follows. Validators have been told to ignore type 1 in the presence of type 2. Well, that kind of sucks because now you don't have a chain of trust anymore. So literally, the validator doesn't see any valid DS record pointing to a DNS key.
Warren, you're not supposed to be laughing. This is a tragedy, not a...
Yeah, we've seen top-level domains fall over for this, and I'm sure top-level domains we can measure because root zone, etc., etc. For lower-level domains, it's a little bit harder to measure, so I haven't done that. But yeah, so this is a problem. So let's look at what the standards say.
Just to clarify, you're changing the DS hash algorithm type.
Just to clarify, I literally add a DS record for type 1 for the new key and for type 2 for the new key. I'm not changing it, I'm adding it.
So you're doing an algorithm roll at the same time?
No, the digest type. Not the algorithm is changed from the KSK, but it's the digest type that's changed. So yeah, in a sense, it's an algorithm rollover in the DS record. That sounds heavier than I meant it to be, but anyway. So let's continue. What do the standards say? So there's a nice RFC, hi Wes, RFC 4509. Now, Wes is not to blame here. He was the editor at the time, and this was supposed to be a boilerplate kind of, right? A boilerplate kind of document that says, now you can use SHA-2 or SHA-256 in DS records. However, Section 3 implementation requirements, validator implementation should, capitalized, ignore DS records containing SHA-1, basically if SHA-2 is present. Now, that actually updates 4035, and I'm a protocol lawyer, right? So this is bad because it doesn't actually say it updates 4035, which is kind of annoying because you first go to 4035 and then you have other documents, but it would be good to know which document updates other documents. So an errata is coming their way. There's some good advice. Well, there's some advice. Zone operators should consider deploying both SHA-1 and SHA-2 based DS records. Keep in mind this was written in 2006, not 2018. Right? And this should be done for every DNS key for which DS records are being generated. Keyword, are being generated. So you add a new key in the zone, right? And so you add a new DS record. The old DS record and the old DNS key are not being generated. That already exists. So I'm highlighting this, because if you follow this to the letter of the specification, you will fail. Your top-level domain will fall over.
Which countries?
Excuse me?
Yes, which countries?
Oh, yes, which countries? So, no, I know the answer, but it's not about that. Ask me afterwards. And it's not necessarily countries. Some of them are GTLDs. Oh, I said too much. Okay, let's continue. So, whether to make use of, and I hate these kind of things, but you have to have them, whether to make use of both digest types and for how long is a policy decision. Hey, escape answer. Right? Policy decision that extends beyond the scope of this document. Now, I understand why it's there, but the problem is, this is operational advice that comes in a regular standard, not in a BCP. So, continuing. We have actually some operational practices on DNSSEC, two, one updated the other, so I'll stick with the latest one. You can either use double signatures, let's ignore that for now, because we're talking about double DS. You can or use double DS. Both old and new DS are in the parent. Old DNS key is then replaced by new DNS key. Okay, this is a quick highlight of what's in that standard. What's in that BCP. But there's no prescription of the prevention of the failure mode when, etc., etc. There's absolutely nothing in there. So there's nothing documented about this failure mode. So I've got a few notes on chain of trust. So I hope it's clear it's a problem. We've seen 3 failures already, and that's only in December, right? And I'm sure that people will, top-level domains and other domains, will have to roll over their key at one point in time. So this is some notes for chain of trust. This is specifically for when I have much time left, and I think I have some time left. Yeah, perfect. So some top-level domains have 2 DS records per DNS key in the root zone. That's absolutely fine. Using different digest algorithms, that's absolutely fine. That works. The highest recorded number, because I can do stats, of DS records for top-level domains since the root was signed was .us with 8 DS records, referring to 4 DNS keys using 2 digest algorithms. There's nothing wrong there. Nothing to see. It all works. The current highest number of unique key tags, and I checked it when I left on Tuesday morning, 3 DS records, all unique keys, same digest algorithm. There are a few top-level domains who have that. Still, nothing wrong here. You basically have 3 chains of trust. Some statistics, we have 1,398 top-level domains that have these chains of trust. In other words, they're signed. 184 top-level domains have self-signed keys, but don't have a DS pointing to it. So maybe they're still part of the cleanup. They will be cleaned up in the future, part of the key role. We have 202 top-level domains with KSKs that do have DS records, but are not self-signed. Now, if you understood this presentation a little bit, these 202 were lucky. They didn't do this algorithm upgrade that Sam Weiler just mentioned. They are not self-signed. That might become in the future. They might still be part of the key role. And then we have 81 top-level domains that have a DS record, but no keys. They have. I need to clarify that. They have other DS record with keys, but they have basically, of all the top-level domains that have secure chains of trust, 81 have dangling DS records, right? They do have other DS records with keys, but they have DS records without keys. Again, absolutely fine. Okay, now, it is a little bit important. I think I understand, but I'm not a cryptographer, I think I understand what the reason for this text in RC 4509 was. Right, you have basically a DS record with SHA-1 and a DS record with SHA-2. RC 4035 says you need at least one chain of trust that matters. So you need to pick one or you need to pick two. Sorry, SHA-1 or SHA-256. Which one do you choose, right? Now, if that advice in 4509 wasn't there, you could basically choose one, right? Now, what if SHA-1 is broken? And this is going to be a very stretched argument, so bear with me for a second. What if SHA-1 is broken, but you still decide to use it? What if SHA-1 is broken in such a way that an attacker can have an online attack, right? An online spoofing attack. Sorry, not online, on-path spoofing attack. And he's able to break SHA-1 in such a way that he can produce a key that results into the same digest, right, as the DS record in the parent. Now, that's so highly unlikely, that's so extreme, that I think that advice in 4509 was a bit overkill, but I'm not a security mafia. There are very security mafia in the room, so I'll leave it to them to stand up and talk to me in a sec. So multiple variations of this idea of having DS type 1 and DS type 2 exist. But the two main things are you have an on-path attack, and SHA-1 is broken in such a way that you have a pre-image, how do you call that, a second pre-image attack. So this is not a collision attack like the shattered problem that we had a couple of months ago. Anyway, the missing advice. So here I'm probably get killed. Be consistent in using digest types in DS record. Right? If you have digest type 1 for your current key, use digest type 1 for the next key when you're about to do a rollover, right? Or if you have digest type 1 and 2 on the old key, use digest type 1 and 2 on the new key. Right? It's actually that simple. Don't rely on your parent to figure it out. Right? Because a lot of top-level domains, and dare I say IANA, right? When you ask us to publish an NS record, yes, we do some checks, sorry, DS records, there are some checks that we do, right? But it's often garbage in, garbage out, right? So don't, and I'm looking at Sam again, don't roll the KSK and the digest type at the same time. You either do one or the other, but not both at the same time. And if there is ever a DNSSEC best current practices number 3, then this should be added, in my humble opinion. Oh, also, I forgot one. It's 2018, so you don't have to use SHA-1. You can use SHA-2 now. I think all the validators that matter, and I know this is a political statement, all the validators that matter support SHA-256. If you don't support SHA-256, you don't matter. Okay. Cool, that's it. I've got 10 minutes for questions. So.
Hi, Roy.
Hi, Wes.
Wes Hardiker, USC, author of 4509. A couple of things. One, I think Sam declared it perfectly. You're doing both a a new key and an algorithm role functioning within the DS, and we don't call them algorithms, whatever, but that's the nature of the problem, and you shouldn't do that. And you're right, it's not documented anywhere. Just for a bit of history with respect to 4509, 4509 came out during the height of the Shaw 1 Cold War scare, because that was right about the time it was looking really dangerous to be in use. And the goal was to get the 4509 out the door as fast as possible, and I actually believe if we look at publication times, it's probably one of the fastest RFCs from initial authorship to out the door, because we were absolutely scared that it needed to be done. So it was actually done between one IETF and the next. It was within RFC within like 3 months. And so I'm not surprised that we're missing advice there at all, that the working group came up with. The one thing that I don't think I saw on your slides, unless I missed it because I was madly trying to calculate it myself, was the number of existing TLDs that only have Shaw 1 DS records now. Because those are the ones that are going to be affected by this problem, right? And if my calculations are correct, which I really don't trust because I just did it very, very quickly, while you were talking, there are two. There are only two that only have Shaw 1. So the chances of somebody hitting this are actually, there's only two. And so we should go write them.
Yes. So thank you. On the first point about the time when this was standardized, I was there and I agree with what you said. On the second point, you're absolutely right. There's only two, but that's in the root. There are plenty more elsewhere.
So Medica Kao, I remember at the IETF 1 or 2 IETFs ago in the DNS OARC group, they were talking about whether or not to have crypto agility and whether or not to have certain defaults. I actually think it's a good idea when you're doing a key rollover to see whether or not a newer algorithm will meet the requirements of the time that a key rollover will be done, because a new algorithm will require one. So I don't think it should be one or the other. And my recommendation for the folks that are standardizing any kind of DNS protocols that deal with crypto is do standardize on certain algorithms, right, and update the documents when necessary. Because this is why people still have SHA 1, right, which is actually ridiculous in today's age.
I agree.
Sam Weiler, MIT, W3C. There may actually be more edge cases in the case of a digest algorithm rollover. We have rules in there that say if you don't recognize that a digest algorithm number, you ignore that DS record. As I look at that, I'm thinking, if I did a rapid cut over to just this new DS record and the key also in the zone at the same time, I have a cached DS record of with the old hash algorithm, and I know it, and the zone becomes invalid. So there could be other edge cases here. This is really an algorithm role, and we really have to go through all the painful steps of treat it as an algorithm role.
Yep.
To what?
I want my camera. Peter Koch-Dienig. Dear Roy.
Dear Peter. Wie geht's?
So not only are you the protocol lawyer, you apparently are an English language lawyer by trying to read so much into the passive present continuous form in that, says the other lawyer, right? In that section.
Actually, the Irish guy.
Michele, we're still at the meta level here. No, so but we've heard about the history and how quick this was. Obviously, this should not be weighed in gold and so on and so forth. The point I was really getting to is this seems to be important in cases where, for some reason, the policy of the operator of the zone or the operator of the zone themselves change. And I haven't checked, but I wouldn't be surprised if that was one of the cases. Because under no other circumstances would somebody who is already deploying one algorithm go back and support 1 and 2, right? So what was called an algorithm role isn't really a role, because for DS you roll in but you don't roll out anyway.
Yeah.
But this is when things go over to another operator and they just execute what they've been doing, like submit 2 different DS records where the previous operator just worked on one, and no matter what version it is, these things can happen. So that is extremely important to look at if you have this handshaking, which may be interesting in so-called emergency backend operator changes and things like that.
Yeah,
thank you.
Thank you. Paul, before you go, just one quick question. Before my presentation, who knew about this? 1, 2, 3. If I say less than 10, is that? Yeah. Okay, good. Because normally I'm the last one to find out. So. Go ahead, Paul.
Paul Hoffman, you know that I was after you because you sent me the presentation. I went, oh my God. So, but go back about 5 or 6 slides to keep going to your to the DNS viz. There, stop.
Yeah.
I want people to notice something, because Sam had said something that I think people might have glossed over. They put 2 DS records in. This is not what you would call a rollover. This was 2 DS records.
Yeah, this is additive.
Yes. It's not just when you're switching from one to another. It's when you think that you are gracefully doing the right thing of putting as much in as you can. That's what messed them up.
Yeah.
So please be, if any of you are going back and going to tell other people we need to be careful, please be careful not to say don't just switch to one, because switching to 2 got them in equal amount of problem.
Oh, sorry.
Paul Wouters. So what I'm not hearing is if we have any advice for resolver implementers where we basically tell them you should, the limitation of dropping SHA-1 for security should only be done on a per key basis and not on a per set basis. Are we giving them that advice or not?
Oh, I'm just here to give you the bad news about the current state of things. Like I said, I'd love to have a discussion about what the advice should be. So I put a few boilerplate advice thingies on there, and in the hope that you come out and actually help with the advice. So well done.
My name is Andrew Sullivan. This is the wrong venue to explore this entire history, but I dimly recalled some of the controversy around this document and this particular wrinkle in it. And it came up more than once, because in fact later we had some other operational practices and so on that also we had a fight about this. And I think the key ambiguity is something that Paul touched on just a moment ago, but I think people need to maybe understand this a little more clearly. And that is, there is this moment, because of the way it says you should ignore ignore cases where you've got that one. That case, because of that, we're actually treating the RR set as having a kind of independent existence of the RRs that are there. And I think that is not terribly clear in the documents. I think that's really where the problem is. I don't know how to make it any clearer, because every time we talk about this, the list explodes, and we don't actually get any text that we know what to do with. But that's where the deep problem is, and maybe that's the place that you're going to have to make some kind of clarification to make it plain to people that the implementation here is actually over the entire RR set.
Yeah. There's something I want to add here. There's also something to say for leaving stuff to operators and not having things like hammered into a protocol like the way it's done here, right? Go ahead.
Joe Abley, Affilias. So we were aware of this because one of the TLDs that happened recently was our TLD, and we were winning that TLD from another operator. So the incoming DS records that were added were for the key to be used at Affilias. The type 1 was there as being used in the old provider who was signing. So it was actually transferring the TLD from one operator to another. And just to give a data point to confirm what Andrew said, that the operational confusion that happened when we started to see validation failures across the entire part of the namespace was entirely down to that misunderstanding, because the idea was we added a type 1 and a type 2, so if you ignore the type 1, it doesn't matter, we have a type 2. Nobody thought that that meant you ignore all type 1s, referring to different key tags as well. That's brand new information. So that was really the point of operational confusion that our people suffered.
Yep. Cool, thanks.
All right, this next presentation is the last presentation before the afternoon coffee break. The next presenter is Joe Crow from Comcast.
Afternoon, Joe Crow from Comcast. I'm an engineer in our core network services team. We do DNS, DHCP, NTP, so we're pretty much tied up with a lot of work every day. At Comcast, we do about 500 billion queries per day for DNS alone. Everything we do is DNSSEC validated for our external and internal customers, so DNSSEC validation does scale. We hear people say, no, it doesn't scale, it's hard to implement. Validating it to implement and validate now is very easy. Every resolver out there has that option to just turn it on. So if you want to validate, turn it on. But you run into a couple issues. When DNSSEC fails, what happens? Well, a company like us, we get blamed pretty quickly. We're blocking websites. Recently, a couple years ago, HBO had came out with HBO Now and just launched it, and DNSSEC failed. We got blamed. Net neutrality, oh my God. Google was failing because they do DNSSEC validation, so people were like, oh, we're switching to a new resolver. That's going to fix this. Well, everybody usually switches to Google. They're doing the DNSSEC validation as well, so it failed as well. The temporary fix is to put in a negative trust anchor at the resolver level. At those points, you want to kind of find out why you want to do that. The woes, we implemented DNSSEC has been known to have some issues when people implement it and want to validate and sign their own zones. So it's, even though it's an authoritative issue, we are the first people to get the blame. People come out and say, hey, it works on OpenDNS, or places that are not doing DNSSEC validation. So they'll be like, why are you breaking my DNS? What are you doing to me? Why are you doing that to me? So the big issues that we look into is when a big domain does fail. When it fails at DNSSEC validation, there could be a major security issue, there could be an operational issue, process issue, technical errors. And in our experience, it's mainly an operational and technical issue. We don't really see that many security issues when DNSSEC is failing, when we fail a site that's DNSSEC signed. We hear a lot of the customer complaints. We get the phone calls, we will get Twitter screaming at us. Again, you'll see it all over the place. You can search for Comcast DNS and hear a lot of things of how we're breaking everybody else's websites, we're blocking. So there's a few options when we're in that state is, do we let the domain continue to fail? Do we turn off DNSSEC validation? Hell no, we're not turning off DNSSEC validation. We put it on for a reason. Or should we put in a negative trust anchor for that one domain, which is going to be the better option. If you know that domain there's an operational error and it can't be fixed quickly and it's costing a big company money, and we're breaking them, well, they're broken and people think we're breaking them, we can put in a negative trust anchor and try to go and make sure that domain is getting traffic the way it should be. So when we implement, and when we started talking about doing negative trust anchors, we initiated our conversation and find out how we're going to do it, when we're going to do it, why would we do it, and then we also figured out our steps, how can we get this negative trust anchor put in for a domain across our footprint in a quick time. And you want to stay consistent with your process. You want to make sure that that process stays the same. If there's some kind of changes, you want to talk to your team and make sure that everybody's on board with that. You want to understand the risks of why you keep keeping a domain to fail DNSSEC. Again, as I said, if it's a technical error, we want to make sure that those people know that their DNSSEC is broken on that domain. So we reach out and let them know from their whois account, support account. We actually have direct emails to .gov because they like to fail a lot in DNSSEC. Go figure. So we allow them time to actually fix the issue. We won't just go in and just say, oh yeah, we're going to put in an NTA, because then we're not doing the correct thing for DNSSEC validation. We're just saying, oh, you know what, it's broken, we know why it's broken, we think we know why it's broken, we'll just put that in. We'll usually update our community and our customers and through our Twitter handle. We used to do it through our DNS.xfinity.com, but now we usually use Twitter and say, yeah, we're aware that this domain is failing and we've reached out to the correct people. We've automated it. I mean, you got to automate. It's one of the best things that's happened to us. We have hundreds and hundreds of servers across our footprint. We don't want to go in and type a command to put in an NTA for every single server. So we have one place, we can just update there and push out to all of our servers, and within minutes we're pretty much in the clear. And then after that domain is fixed, when the people that have a broken domain reach out to us and said, yeah, we fixed issue X, Y, and Z, we'll then go in and remove that negative trust anchor. That way DNSSEC validations work in the way it's supposed to. So troubleshooting, most everybody in here should probably know how to troubleshoot. Can you dig it? If it's a serve fail, you usually can tell if it's a serve fail and it's a DNSSEC problem by doing a plus CD afterwards. And then I personally test with other DNSSEC validators just to make sure it's not our DNS resolvers that are breaking. There might be an issue that we're unaware of. DNSViz is your friend. It's been a godsend on some of the things that we need to look at, and to be able to go to a customer and say, no, we are not blocking you. Here's proof. Here's a third party that is giving you a breakdown of where you're broken. And usually those people will understand at that point. And then if it's a key rollover issue with a customer, we might be able to just flush our cache and be able to let it go through a little bit quicker and not have to do anything else special. And this is quick talk, so some light reading material, and that's it. Sorry for... Any questions?
Paul Hoffman, and this is not a question, but the bad idea fairy just visited me. It would be good to know after the fact, when you, a large validator who has, since you guys actually you promoted the ability for people to understand how you're doing negative trust anchors in the IETF, caught a lot of flack for, not as much flack as you get for blocking HBO now, but you caught a lot of flack in the IETF by people going, oh, that's bad, that's bad. It would be useful to the people who believe that negative trust anchors are bad to know when they have been used. Because hopefully you're using them rarely and for a short period of time, that's fine.
Yes.
So the bad idea fairy that just visited me, and I'm now looking at you, Warren, because you work for the other large vendor that does this, it would be nice if there was something like certificate transparency, so that you can say that only gets filled after the fact, so once it's over, where you can say, we had a negative trust anchor from here to here. And it would be very interesting to see if those times didn't match up. I think, it wouldn't be useful to the world, but it would be very useful to researchers if we had time frames that we could match up of the various people, large and small, who felt like they had to do a negative trust anchor.
That's worth looking at.
Rafi Wakama, thanks a lot for this. Just one question. Do you have some statistics or some feel on the need on putting in negative trust anchors? Because I have the feeling, at least from the stuff that I do on my resolve, it's gone down a bit.
I can say within the past year, the amount of times we had to put in an NTA has diminished. People have been pretty well, doing well with fixing the issues pretty quickly. So we don't, the statistics, we don't really have statistics on how often we've done it, but from my personal experience, we've been pretty low on how many times we need to put in an NTA from 4 years ago when I started.
Okay, thanks.
I'm adjusting the microphone for Warren. This is Robert from PCH, Robert Martin Leciende, sorry. You are obviously using some mechanism that cannot be automated and finding out which negative trust anchors to use, because otherwise somebody might have put it into bind and not and whatever. But how do you know that the answer you're getting through your back channels is actually authoritative?
We'll actually reach out to the people the website that's broken. So we'll reach out to their administration or the people that are running their websites and say, are you aware that you're failing DNSSEC? That part of it's not automated. We have to actually do some legwork at that point.
So basically you call them?
We call them, we will email them if it's a long amount of time.
How do you email them?
I'll usually go to whois and find their,
No, I mean if DNSSEC is down. Okay, I shouldn't answer that question.
There have been times where we can't reach them because DNSSEC's broken, but they might have a different domain that's in their whois. If it's a different domain in their whois and a different way to reach them, we'll reach them that way. Picking up the phone is the other way. We have. For .gov, we have an IT help desk that we can email, and they'll reach out to the correct people. And at that point, those things are not automated. We can't automate that, But when it comes to implementing the NTA itself, that's very automatable.
So reaching out by email, phone, or whatever, that's pretty good. And Comcast is important enough with the user base they have, but it doesn't scale. Is there some way we can make it scale? So, I mean, all operators decide to chip in and generate a web of trust of negative trust anchors.
It's on you. It's up to you. If you wanted to put in a negative trust anchor, it's on the people that are actually running the DNSSEC validators.
No, I think if people shoot themselves in the foot, it's their fault. So I don't care. But I don't talk to customers.
We have a lot of customers, and when it comes to Comcast, it is one person turns into a million people, turns into millions of people, and if it's a big domain or if it's a .gov that people need to telecommute into, and those people can't work. We're a little bit quicker of trying to put in an NTA for those specific things. If it's a small little mom and pop shop website, we're going to let it fail. We're going to try to let it fail as long as we can until we really get,
That sounds absolutely politically correct. Thank you.
Yep.
So, Robert, how tall do you think I am?
Wait,
So yeah, Warren Kamari, Google. So yeah, there had actually been some previous discussions on maybe sort of having a list of shared negative trust anchors that people could subscribe to. But that got really scary really fast because, who gets to decide what can go on that and why can't the attacker just do it? As for automating it, the number of times that I think in general people actually implement these is so small that you really want somebody involved in poking at stuff and doing things. I mean, yes, we have this feature, but we really don't like to use it because, it requires work. You should also just let people fail. However, when it's a huge site like NASA, for example, is the standard example, and it's something that is fairly clear that it's just a DNSSEC screw-up. For example, there's a new KSK, but they didn't update the DS, and you can still see that, or the other way around, where you can see that they rolled something and it apparently was a botched key roll, then it's sort of potentially we'll do this for a little bit. But in general, these almost never happen.
Agreed. We want to keep it in as, that NTA in there for a small amount of time. We don't want to keep it there for a long time. And you're correct, automating something like that is, you want to have that discussion with the people because there might potentially be a security issue going on. And if they're not aware of it, and even at a key rollover state, that short time that NTA is in there, they're vulnerable. As well. So you want to make sure it's correct. Thank you.
Okay. So Ray Bellis, ISC. I was going to come up and play the idea of, play the role of really bad idea fairy and suggest federated feeds of NTA zones. So thank Robert for coming up and doing that for me. So in which case, it just leaves me with thank you for quoting my T-shirt, which says, "Can I dig it?" Yes, you can. Thank you.
I love it.
Joe Abley, Affiliates. I was interested to know, you mentioned that in some cases you can just flush your cache because whatever problem has happened has been fixed by whoever caused the problem, and all the lingering problem is just that the caches around the place contain the bad data.
Correct.
How often do you think that is a problem in your experience? Is that usually the case that you need to do a cache flush?
That'll be a quicker fix. When we see that DNS is failing, that would be one of our first troubleshooting steps is it really failing? Is it because, the cache is bad? Let's flush that domain and see if that's really going to fix that issue. And that's one of our troubleshooting steps. All right. Thank you.
Okay. Thank you. That concludes that session. We are, again, running slightly ahead of schedule, but we're going to go along with our regular timetable and resume at 4:30. I believe coffee may not be available just yet, but will be very shortly. Thank you.